let's just do a quick review and look at, try this problem, and then I'll give you two more to try. This is when the switch is closed.
Professor, what does that say right above 24V?
Oh, I'll
Is
get
that
to that. It's V sub S. It's a subscript. It's saying, just like we could name this R1, we need to name, if we want to name a power supply, we're giving it the designator V sub S, S for source.
S for what now?
Source, the source of the power, source of the
Okay,
voltage.
thank you.
So try those three problems, and then we'll go over them and see how you made out. Once you're done, just send me a chat message that just says I'm done. Just so that I'm not sitting here waiting for everybody that's already done to be done. Looks like about 9 of you are done so far. Half of you. Okay, looks like most of you are done. So let's take a look at it and see how you made out. We know that V sub S, the source voltage, is going to be 24 volts. We know that R1 is 300 ohms. One thing I didn't mention, that's always a good idea to do, and we just sort of jumped into it. Anybody ever taken a first aid course? No one? Okay.
Yep.
If you've ever taken a first aid course or a CPR course or anything like that, one of the things that they teach you is when you come upon a scene, whatever it is, you don't just jump into action. The first thing you do is you analyze what you're looking at. So, you wouldn't want to do CPR on somebody if there's an electrical wire running on top of them. So you want to analyze what's there. You want to look at and get your data. That's not a bad idea when it comes to solving problems. So the data that we're given that V sub S is 24 volts and R1 is 300. You look at this problem and go, yeah, but that's so obvious. It's obvious on this problem because it's a simple problem. But later in the semester, when we get into series circuits and parallel circuits and series parallel circuits, it sometimes pays to write down what you know so that it makes it a little bit easier to figure out what direction you're going to take to solve the problem. So since we know the voltage and the resistance, and we're asked to find the current, we know we're going to use a formula that says I is equal to something. And if we think about Ohm's law, the only something we've got is V over R. All right. So I've got 24 volts divided by 300 ohms. Remember, we're always going to show the formula, the mathematical substitution into the formula, and now we're going to do the calculation for the results. And that works out to be 0.080 amps, or if I want to, I can convert it to 80 milliamps. Okay.
On a test, which one would you prefer? Would you want it as amps or milliamps? I did both.
Unless I specify otherwise. Oh, let me say this about the exam too. Unless I specify otherwise, you can put down whatever you want. Somebody asked me, which unit do you want? And I just said, you choose. On an exam, however, if I say to you, specify what is the current in milliamps when the switch is closed, all right, then you've got to give it to me as 80 milliamps. When we get to series circuits, parallel circuits, series parallel circuits, there are going to turn out to be multiple ways that we can solve problems. If I just say solve for the voltage or whatever it may be, you can use any approach you want. But if I say to you, solve using whatever I specify, what I'm really saying is show me that you know how to use that method. And if you don't use that method, that doesn't show me you know the method. All right. So if I specify a method, then you've got to use that method. If I just, like here, I just said, calculate the current. There's only one way we can do it, but if there were other ways, you could solve it any way you want. All right. So that's just something to keep in the back of your mind. Okay. Any questions on this one besides the one about what format? Okay. The second one, we're told that the current is 20 milliamps and the resistance is 680 ohms. And we're looking for the voltage. So we've got the V equals formula. And again, Ohm's law has only one formula that we can use for V, and that's I times R. So now we're going to have 20 milliamps times 680 ohms. And that works out to be 13.6 volts. Let me just say a word about the let me finish this up, and then I'm going to talk about how you enter stuff in on the calculator, because this is where people get this right, they get this right, and then they end up with the wrong number. And we'll talk about the calculator in a minute. I'm just sort of kind of getting to that. Okay, so find the current when the switch is not pressed and when the switch is pressed. So what kind of switch have we got here? Anybody remember what that's symbol for?
NC.
NC, what kind of switch? It's an NC. Who said it?
NC single.
Okay. Push button, toggle.
This is a push button.
Push button, yeah.
Yeah, this is a push button switch. And NC stands for
Normally closed.
normally closed. That means the contact is there. Remember, the normal is the not pressed position, not pressed condition. So when it's not pressed, it's normally closed, which means the contacts are there, which means we have a full path for current to flow. If I push that, that puts the bar over here somewhere, which means we've got a break here and a break here. The circuit is open, and we don't have the complete current path we need for the current to flow. So we can see that when I press the switch and we break the circuit open, what we get is 0 amperes. There's no calculation. We just know there's a break in the circuit. Okay. Give me 1 second. Okay. So now we can calculate the current. So we know that we're using the I is equal to V over R. That's my formula. My voltage is 10 volts. My resistance is 22 ohms. When I do the math, that works out to be 0.454 amperes. Or if I move the decimal point 3 places to the right, 454 milliamperes. Okay. All right.
So
Let's talk about the. Go ahead. Question.
yeah, on that one I put 0.5 because it was another 5. Would that be wrong?
Yeah, you want to hold at least as many places as you've got in your value. So at minimum, this would be 0.45 because you have 2 significant figures here, 2 significant figures here. That means you want to express your answer to 2 significant figures.
Okay.
I think I was wrong too because I did 4 or 5 like with the line over it. So to signify that it's like going on that way towards infinity.
Yeah, that's fine. You know, I take a different approach. You know, you get into the rules of people who teach physics. One of the professors who used to teach physics, a student came up to him. I was standing there, just happened to be in the room. And the student said to him, well, how many decimal places do you want? And he said, how many does your calculator show? That's what I want. And I thought about it and I said, yeah, okay, that's nice for a theoretical physics class. But if I had this and it was, let's say it wasn't 4545 repeating, but let's say it was 454843742241 milliamperes. The realistic part of it is, as a technician, you're never going to have an instrument that's going to be able to measure it to that accuracy. So my question is how accurate is the instrument that you're going to measure this with? Because if you're doing a calculation, right now we're doing calculations for the sake of doing calculations to learn this stuff. But when you're working and you have a situation like this and you've got, okay, I know that across this resistor, I've got 10 volts. So I want to find the current that's flowing through here. And I do this calculation, it turns out to be 454 milliamps. So if I put a milliammeter in here, and you guys, I think, did this in lab, if I put a milliammeter in here, I'm not going to be able to measure to 8 decimal places. You'll probably be lucky to get to 3. So my rule of thumb is I don't generally work more than 3 significant figures because that's all you're ever going to be able to measure on an instrument. Okay, so that's where I come from on that one. Okay, let's talk about the calculator for a minute. All of the scientific calculators, if I wanted to, let's say go back to this problem where I had 20 milliamps and 680 ohms, okay? So we had V is equal to I times R, it was 20 milliamps times 680 ohms. And we want to put that in our calculator. What you're going to do, and did Professor Atwood spend time going over the calculator at all? Yes, no?
I don't
No.
No.
No. Okay, let's just go over it quickly then. We know that the prefix milli means times 10 to the minus 3.
Mm-hmm.
So my power of 10 is minus 3. So if I put that in the calculator, I'm going to put in 20. Okay. Now, on the calculator, the times 10 to part, this part, either shows up on the TIs as EE or on some other calculators, like my Sharp shows it as an EXP, and my Dollar Store Deluxe calculator shows it as an EXP. So what we're going to do is we're going to hit the EE or exponent key. So that's the same as if we put in times 10 to the whatever. And then what we're going to do is we're going to put in the 3. And on your calculator, there's a change sign key. And the change sign key usually looks like plus minus. Okay, so that's going to show up. What should show up on your display at this point right now is 20 little script times 10 and minus 3. All right. Now what I can do is let me just do this. So this is a calculator key. This is a calculator key. Now we can hit times, which is a calculator key. And then we enter the 680. And we hit equals or enter on the TIs. And what should show up on the display at this point was 13.6.
I just a quick
One
question.
second. It's really important you use the EE and the exponent. There is a key on the calculator that's like times 10 to the whatever, times 10 to the X, I guess.
Mm-hmm.
Don't use that.
Are we only putting one E or both, or are we putting the E twice?
No, it's a key that's labeled EE.
Yeah, I clicked that and it just showed one E. That's okay.
On the display.
Yeah.
Yeah, no, you press the EE key. So on a display, if you use the EE, you're liable to see 20 E minus 3. Is that what you're showing?
I just have 20 E and then 3. Am I supposed to put?
You didn't hit the change sign key yet.
I don't think I have a change sign.
On the TIs, look for, if I remember right, the TIs might just have this.
Yeah, I have that.
That's a change sign key.
Okay.
Yeah, but it's different. You don't put the 3 first and then the change sign.
Change sign 3.
On the TI, you have to put minus first, the sign, and then 3.
Mm-hmm. Yeah.
Okay. It won't let you change sign after? I don't have it. Or maybe I do have a TI. Hold on.
I have a TI, a virtual TI, so I can show it if you let me share the screen.
All right, hold on one second. You have it. Okay. Where are we here? Let me pause my share. And All right, see if you can share now. Is it letting you share?
Yeah. Do you see that?
Yeah. Okay.
Okay, so so you put the 20, and then the EE is right here in blue. So you
Okay.
press second, and then EE. It displays only one E, and then -3. And then it was times 680.
And there's your 13.6. So I don't know how many people, I assume that most of you have TIs
Mm-hmm.
because of the math course. Thank you, by
Mm-hmm.
the way, Ronnie.
No problem.
Yeah, thank you, Roni.
So, but the important thing is that you use the EE or the exponent key. If you just use, there is that, oh, could you bring that back up again, Ronnie?
Yeah. So you want to say not to use 20
No,
times
no.
10.
Yeah, you don't want to use the 20 times 10 to the, above the, it's a second function log key, 10x. You don't want to use that. For some reason, sometimes it gives you the right answer, sometimes it doesn't. I've had students that in the past have had, they'll do that, and it logically says, oh, I should come up with the right answer, but somehow it does not come up with the right answer. So you always want to use the EE, which is the second function apostrophe, just above the 7, and in place of the times 10 to the. Okay, thank you.
It doesn't work when this number is in the denominator, because first it does the divide by 20, and then it multiplies the whole number by 10 to the negative 3.
Yeah. Yeah. So I wonder, I guess if you put parentheses around it, it might force it to do it.
Yeah, if you do
Yeah.
parentheses, it works, but then you have to remember to do the parentheses.
Parentheses, yeah.
Yeah.
Okay. So the bottom line here is that whether you're using a TI or whether you're using one of the cheap calculators, whether it's a Casio or the Dollar Tree calculator or whatever, you always want to use the EE or the exponent, so that this in here is doing the times 10 to the n. And the n you're going to put in next. And then for the TI, we just figured out the negative sign has to go before the 3. For the cheaper calculators, I believe you can put in the 3, then the change sign. As a matter of fact, you can put in the 3 and change sign. All right. I can't emphasize this enough because people come out with strange numbers. So, okay. So,
Okay, Professor. Can we say milliwatts?
say that again.
13,600 milliwatts. Can we say like that? 13,600 milliwatts. Can we say?
Yeah, usually, well, first of all, it would be millivolts.
Yeah.
So you want to do this, 13,600 millivolts. Usually, you try and keep this number, whatever the result is, to a number that's like less than 100, unless you're working to a specific unit. The only place I would use this is in millivolts. If I had this and I was going to multiply it times 4.7 k ohms, this is times 10 to the minus 3. This is times 10 to the plus 3. And if you remember from math, if I multiply 10 to the minus 3 times 10 to the plus 3, they cancel. So I might do this just to make my calculator life easy, because then I don't have to put this in or this in. They cancel. It would just be 13,600 times 4.7. All right. But generally, you try and keep your answer around less than between 1 and 100, basically. Unless you're specific, have a specific reason other to do that. Okay. All right, so let's do a couple more and then I'll go on. So let me do, I just realized I forgot one sample.
You said M is motor, right?
Yeah, that's a motor, the symbol for a motor. Okay, so what we want to do is determine the resistance of the motor when the switch is pressed if the motor draws 100 milliamps from the source. So see if you can figure that one out. Okay, I'm just sending out a quick poll. I'm curious to see who's using what calculators. So just send me a link to whatever calculator you're using. We got 16. We got 19. Oh. Okay. So it looks like the majority of you are using TIs. So what I will do, Ronnie, if you get a chance at some point, just send me a link to where you got that TI display calculator. You can send it as an email or whatever.
Just download it from TI website, but it has a 90-day trial, and then probably you have to purchase it.
Okay.
I'll send you the link.
Okay, thank you. All right. All right, so just a quick reminder that for the exams in that, you will have to use a calculator. So if you're using your phone, that's fine for now and fine on homework. But before the exam, you got to come up with a calculator. And the exam will be probably in a week or 2 weeks. Okay, so let's look at the solution to this one. So we know that ES is 40 volts. The current is going to be 100 milliamps. So Ohm's law says that R is equal to V over I. So I have 40 volts divided by 100 milliamps. If we think about how we're going to put that in the calculator, we're going to enter it as 40 divided by, all right, so that's a calculator key. 100 EE minus 3. TIs have enter or equal?
Enter.
Enter. I have a TI calculator. I'm going to have to drag it out somewhere. And what that should work out to be 400 ohms.
Yeah.
If I did the math right.
Mm-hmm. I got the same answer. It's just that I converted milliamps into amps at first, so I ended up with 0.1.
Sure, that works. That's what I talked about when we were doing unit conversions. I was talking about the fact that you may want to change. Whoops. You may want to change units, get rid of units. Like if I got no prefixes here, you might want to have no prefixes here by shifting the decimal point so that you just plug in numbers. Or if I had, something in the top with a prefix, you might want to shift to get the same value, one positive, one negative, and they can, or the same top and bottom, so they cancel. We're multiplying. We want them to be the same but opposite polarity. Okay.
Excuse me, Professor.
Yeah.
When you say switch is pressed, there is current flow.
Say that again.
When switch is pressed, there is current flow through the.
Yeah, so that's the reason I said when the switch is pressed. If I don't have the switch pressed, so again, this is a push button switch, except remember, this is the one that's now normally open. Normally open means there's a break in the circuit. If there's a break in the circuit, we don't have that complete wire current path for current to flow. So there would be, in other words, in the switch position shown here, this would be 0 milliamps. When I press the switch, now the switch connects from this bubble to this bubble, completing the path, and we get 100 milliamps.
Can you switch it up in the previous question?
Yeah, I think on the previous question you put the
Yeah.
answer on the different one.
But
Yes. Yeah.
so in
Find
this
the
one,
current.
when the switch is not pressed, it makes the connection, so current flows. When I press the switch, the bar, which is now here, moves to here, and we have a break and another break, so no current flows. So you have to be very careful. That's what I'm trying to do with these problems is you have to really look at what you've got. This one, as Natasha pointed out, was NC, normally closed. Normal is not pressed. So when it's not pressed, it's closed, making connection. This one, if you look at it, is NO, or normally open, meaning when it's not pressed, it's in the open position, meaning that there's a break in the circuit and current cannot flow. Starting to make sense a little bit? Okay, so you really have to look at the switch. You can't just say, oh, it's a push button switch and solve the problem. You have to decide, is it a push button switch that's normally open, or is it normally closed? And what's the problem saying it wants? Is it when the switch is pressed or when the switch is not pressed? And what does that mean over here? Pressing the switch, does that mean I complete the circuit or I open the circuit? So you have to think about what you're looking at. Okay? That clear up that a little bit? All right, let's do this. Let's look at this one. Try that one. Find the current that's coming from the source, the 24-volt source, when the switch is in the up position and when the switch is in the down position.
Mm. Hmm.
Okay. Let's see how you made out. Trying to download the TI calculator, but it looks like it's going to take a while. Okay. So when the switch is in the up position, what's the current going to go? It's going to leave the source and go where? Let's look at the current path. Where is it going to go if the switch is in the up position?
It's gonna go to R2.
Yeah, the current's going to go through the closed switch. The current is going to go through R2. Now you may get it here and say, oh, well, it can go this way and it can go this way. So why can't it go this way?
Wait, what's the question?
So you may get to this point right here and say, oh, I got a split. So the current could go this way or it could go this way. And my question is, why can't it go up into the bottom of R1?
Because that means it's not making a full like a full connection back to the power source.
Yeah, if you look over here, we have a break in the circuit, right? This is where normally the switch would contact. But right now, since the switch isn't in this position, there's no way for the current to get back. So all of the current has to go this way and back to the source. So my current, which I'll label I, follows that path. So now if I said I is equal to V over R, for all intents and purposes, R1 doesn't exist in the circuit. Because of this open over here, as far as this battery is concerned, R1 doesn't exist. The only thing the battery sees because of the switch is R2. So I'd have 24 volts divided by 3.3K. So if I grab my handy dandy slide rule and say 24 divided by 3.3, 7.56 milliamps. Does that sound about right? Somebody come up with that?
7.3 or something, I guess.
I got 7.27, et cetera, et cetera. But
oh, you know why?
I got the same answer.
24, and I forgot to divided it by 3.3. 24 divided by 3.3. How about 7.26? Yes, no?
Yeah, that's what I got.
I got 7.27, but it's fine. Just a question.
Yeah.
Why, how would we know whether or not we should be converting units in regards to like the ohms here?
Oh, you mean, so if I was going to enter this, I would enter this as 24 divide by, again, that's a calculator key, 3.3 EE minus 3. Oh, not plus. Wait,
Yeah,
wait.
wouldn't it be
It's K
plus
ohms.
here?
It's K ohms. Yeah, I'm back stuck. I was thinking of the answer. So this is EE3 because it's K ohms. And then divide by enter. So this is just going to be enter. Now, in the calculator, you have what's called floating, scientific, and engineering notation.
Mm-hmm.
Floating, this would show up as 0.000726. In scientific notation, this would show up as 7.26 E minus 3. In engineering notation, this would point out as 7.6 E minus 3. If you remember when we spoke about scientific notation, we said the rule for scientific notation is we wanted to have one digit to the left of the decimal point. So we got that, even though the prefix is minus 3, which is milli. In engineering notation, it turns out to be the same thing. We have 7.26 E minus 3. 7.26, we still have one digit, even though we forced. Remember, engineering, this is going to be a multiple of 3. All right, and we'll do a problem with that. You can go into your calculator and in your settings, be able to select whether you want floating, scientific, or engineering. If you put it into engineering mode, it'll automatically force it to a prefix that's a multiple of 3 or 0. So it would be either like minus 6, minus 3, 0, plus 3, plus 6, plus 9, so on and so forth.
Yeah, it's under the mode button.
It's on the mode button?
Yep.
So you can set that up to do that. And that makes life easy because now you're always in engineering mode. All right, so in the switches in the down position, you're going to be where we are there. So now, what's in the picture and what's basically gone?
Only R1 is there now.
Yeah, only R1 is in the circuit. This bar is no longer there. It's now down here. So we've got a break in the circuit over here, which effectively takes R2 out of the picture. So now my current path is going to be leave the source, go through the switch, can't go up this way because that's not there anymore. The bar is now down here, through R1. When we get to the bottom here, we may think, oh, well, it could go this way, but it can't because the switch is now open. And now it's just going to go through R1 and back to here. Try and get this in your head. all right? We're always going to look at and think about things in terms of voltage across something and current going through something. So we would say over here that there is 24 volts across R2. Let me just see something a minute. Okay, so we got 24 volts across R2, and there is 7.26 milliamps of current going through R1, R2, excuse me. It's always voltage across and current through. All right, voltage across and current through. Okay, so now let's look at the switch in the down position. So in the down position, we have I is equal to V over R. So I have 24 volts across 3.3K. And, no, not 3.3, 1K. This was R1, not R2. And that works out to be 24 milliamps.
Hello, Professor.
I'm listening.
Sorry, just for the last thing is that when the switch is in like the up position going through R2, I see that your answer is like 7.26, but I keep getting 7.27 over my calculator. Is that like okay?
I'm getting the same thing. That's why.
7.26 came from my slide rule, which hasn't got the accuracy. So let me just see what it is on the calculator. 24 divided by 3.3. 7.273. Yeah, okay.
Okay.
So okay, so if I go to the TI, let me share a screen. I would enter that as 24 divided by, and now we want to make it 1K, so it's 1 second function EE. Oh, now I know why I remember why I don't like TI calculators. And it powers 3, and then we hit enter. And it comes out to be 0.24. Now, if I go to mode, and over here in, you can either say scientific or engineering. If I put that in engineering notation, and now go back to, so now if I do the same thing, let's see if it comes out in milliamps divided by 1. And it comes up to be 24E minus 3. Now, do not, I will tell you with this up front, do not write your answer as, let me go back to this screen for a minute. Do not write your answer as 24E minus 3. Or, so certainly I'm not going to accept that. And the other one that drives me even crazier is 24 minus 3. All right. That's saying take 24 and raise it to the negative 3 power, which is not your answer. So that's not going to work. So if you're going to put it in milliamps, write it in milliamps. One other little bit of a rant about TI calculators, and I said, now I know why I don't like TI calculators. What kind of calculator is this? TI what?
That's 84 plus C Silver Edition.
Yeah, but I mean, a business calculator, a scientific calculator, general purpose calculator?
Graphing calculator.
It's a graphing scientific calculator. Scientists tend to use powers of 10 a lot. A lot. If I look at my cheap Casio, or actually if I look at my Dollar Tree calculator, the exponent key is right there. It's a main function. If I look at my Casio and my Sharp, they're main functions. Where's your exponent key on a TI? As a second function. So every time you want to put in a power of 10, you got to go second function exponent. If it's a scientific calculator, why isn't it a primary function? Rant ended. Okay. So we've got that. I can show you how to use the TI. Any questions on solving problems? Any questions on how the switches work? The normally open switch, the normally closed switch, the two position. Remember, this is, what kind of switch is this? We said that this was a normally open push button switch.
We're seeing your calculator.
Oh, thank you. Okay, so we said this was a normally open push button switch. We said this was a normally closed push button switch. What kind of switch is this?
Single toggle switch.
Single, it's a toggle switch, I agree with that.
Single toggle, single pole.
Okay, so it's single pole,
Single throw.
single throw, right? One pole it moves, only one place it can go to. So what is this guy?
Single pole, double throw.
It's a toggle switch to start out with, and what did you just say?
Single pole, double throw.
Single pole, double throw. It's got one pole it moves. It's got two places it can go, either up or down. So it's double throw, single pole. Okay? So any questions on anything we've done today in terms of calculations, the calculator, the switches, powers of 10, whatever?
No.
Okay. I will email out a homework assignment. So check your email. And we'll go from there. All right? Because we're just about out of time. We're out of time.
Okay.
All
Last question, Professor.
Yeah.
When you give us the exam, like I know that it's like in like a couple of weeks or whatever from now, will you give us like, I guess like a topics list of things that we should definitely review?
General terms, yeah.
Okay.
Yeah, I will do that. And I'm not sure whether I'm going to do the exam virtually. Professor Atwood said he would proctor the exam during the lab period. So I may do it as an in-person exam and he can proctor it.
Okay.
So we'll see where that goes. I haven't made that decision definitely yet, but I'll let you know. And I also will try and let you know at least 2 weeks in front of the exam. So,
Thank you.
all right. Okay. If there are no further questions, we'll see you all on Thursday morning.
Okay. See you
Have a
later.
good day.
Have a good day.